Look at the exact equator of an electric dipole. Here, the electric field is actively pushing charges, yet the electric potential is exactly zero. To understand why, we need to define what potential actually is, the work done per unit charge. For a single point charge, you can see the formula relies on a straightforward ratio of charge over distance. Notice what isn't there: direction. Potential is a pure scalar quantity. There are no vector arrows to track. By treating potential strictly as a scalar, we strip away the geometry. Complex, multidirectional physics problems instantly collapse into basic arithmetic. This diagram shows a standard electric dipole, two opposite charges separated by a tiny distance we call 2a. The dipole moment vector, p, always points directly from the negative charge to the positive. When we measure the potential at a distant point p, the formula looks like this. Pay close attention to the denominator. Unlike a single charge, a dipole's potential decays at a rate of 1 over r squared. The math shifts depending on your angle. If point P lies flat along the positive axis at 0 degrees, the cosine of 0 gives us maximum positive potential. Swing around to 180 degrees on the negative side, and we hit maximum negative potential. Back to our opening paradox. At 90 degrees on the equatorial line, the cosine of 90 is 0. Because this point is perfectly equidistant from both charges, the positive and negative potentials are mathematically equal. They cancel out completely. Let's test this. If you double your distance from a dipole, what happens to the net potential? Take 3 seconds. Because of the r squared denominator, the potential drops to exactly 1/4. A dipole's influence fades incredibly fast because those two opposite charges are constantly working to cancel each other out over long distances. We can scale this logic up to systems with dozens or hundreds of charges. Think of it like pooling money. If 3 friends chip in different amounts, you just add the numbers together to get the total. Charges work the exact same way. This is the principle of superposition. The total net potential at any given point is simply the direct sum of the individual potentials from every charge in the system. But you have to follow the golden rule. The mathematical sign of each charge must be explicitly included in your algebraic addition. Let's run a calculation. We have a positive 4 microcoulomb charge and a negative 2 microcoulomb charge, both 2 meters away from our target point. When we plug these values into the sum, the negative sign triggers a subtraction, resolving our net potential to 9,000 volts. Calculating potential for massive charge arrays is just an accounting exercise. You tally up the positive and negative magnitudes. 0 vector diagrams are required. This split-screen comparison details exactly why our opening paradox exists. Electric potential on the left is a scalar that drops off at 1 over r squared for a dipole. The electric field on the right is a vector that drops off even faster, at 1 over r cubed. If you encounter continuous objects like charged rings or solid spheres, this exact same algebraic summation simply scales up into a calculus integral. The scalar rules remain identical. Here are the core formulas: the dipole trigonometric equation, the zero potential equatorial rule, and the superposition arithmetic sum. Trust the scalar math. Let it eliminate the spatial complexity for you. Take these formulas and immediately start applying them to practice problems to lock in your mastery.